Okay, and with that, good morning everybody. Welcome back to Calc 2. Plan for today is, as promised, I have a standard 7 quiz ready for you. And then we're gonna do something a little bit different today and have some fun talking about factorial functions. So after some alliteration. Got my usual office hours for the next few days. 11 to noon today and 1 to 2. And same for Tuesday, Wednesday. And as far as homework goes, no homework. No, nothing out on web work at the moment. No quizzes coming up. Take some time to try and enjoy life, or at least focus on your other classes for today. Don't worry, there'll be more coming Wednesday. Yes, Kate.
When will you have the exam graded?
Good question. When will I have the exam graded? I should have that. The goal is to be done grading exams by the end of the day tomorrow. So I should have those passed back Wednesday morning. Also a little bit behind in retest grading, but I'll do my best to get those back to you as well. And fortunately, what with the usual chaos of Parents Weekend added to other things going on in my life, I didn't quite get them done over the weekend, but should be done tomorrow. And I'll update Canvas with everyone's mastery totals as well once the exams get ready. Any other questions or comments? I just realized I forgot to get a joke of the day ready. Does anybody have a good Does anybody have a good joke that they like to tell? All right, fine. Can Dr. Arn handle working with trig functions? Of course he can't. Okay, and with that, we'll go ahead and pass out the standard 7 quiz. So, as usual, go ahead and take a few minutes to work on this. Choose 2 integrals for you to evaluate. Good luck. You got this. Oh, was he maybe perhaps plotting something? Oh, it's a classic. can go ahead and take a few seconds to finish up your puzzle. And pass your quizzes in, please. Quizzes in, please. Thank you, Ken. Thank you. Thank you. Alrighty. So, question. When I write that on the board, 3 with an exclamation point, what does that mean to a mathematician? It could mean that it's a very excited 3, like 3! But the exclamation point in math is often used to indicate something else when you put it after a number. Has anybody seen this notation before? James?
Factorial.
Yeah, we would call this 3 factorial. So what does it mean to take 3 factorial in this case, James?
So the operation is to take 3 times 2.
Yeah. You start with your number and then you multiply it by all of the integers counting down from that number to 1. So in this case it would be, starting at 3 would give you 3 times 2 times 1, or 6. And what I want to talk about today is we're going to start a new standard. Well, we're not actually starting a new standard. We're kind of going to take a one-day diversion in which this week and the week after spring break, we're going to be focusing on looking at applications of why do we care about all these integration-taking tools that we've seen so far. And what I want to do today is to start by looking at one of those by seeing how does this idea of taking the factorial of a number relate to some of the integration stuff that we've been looking at. 6. 1, 2, 5, 6. So, in general, when we talk about factorials, we're going to say that the factorial of number n is defined by the formula n factorial is going to be equal to n times n minus 1 times n minus 2 times n minus 3 times, and then you just keep subtracting 1 and multiplying by the new number you would get, working your way all the way down to 1 in the end. Just so you all know, Dr. Gerstle, why does this not say standard 8 at the top? It's because I decided I'm not going to test you over this topic. Doesn't mean it's not a cool, fun topic, it's just that I couldn't think of good questions to actually ask you all about it. So instead, this is going to be kind of a one-day, hey, take a look at something cool that happens in math. So, looking at a few examples where we would get that 3 factorial using this formula of start with 3 and keep multiplying by numbers all the way down to 1 is going to end up giving us 6. So, Phoebe, how would we calculate 4 factorial? It's going to be 4 times 3 times 2 times 1. Well, we already know this is 6. And so if we take 4 times 6, this would come out to 24. And then we could take 5 factorial, would be 5 times 4 times 3 times 2 times 1. And if that looks tricky to actually go out and evaluate, because there's just a lot of numbers at this point, keep in mind, we've already done most of the work for determining what 5 factorial is. Because we already know that that 4 times 3 times 2 times 1 is just 4 factorial. So if we write this out as 5 times 4 factorial, we just end up with 5 times 24, which is 120, I believe. All right, James, do you happen to know what 0 factorial is equal to?
1.
Hard to trick this guy. Turns out we define 0 factorial is equal to 1. And this is just a definition. This isn't because of but Dr. Gerstle, 0 is already smaller than the last number here. How do we deal with that? Well, that 0 factorial being equal to 1 is going to be something that's very useful for us later on. But this is just by definition. You have to define 0 factorial in a special case. All right, James. That one didn't get you. What's 1/2 factorial?
I don't know.
You don't know? Disappointing. I can't believe, James, that you didn't know that 1/2 factorial comes out to square root of pi over 2. This is true, by the way. 1/2 factorial we can define to be, or turns out to be equal to square root of pi over 2. But Dr. Gerstle, how do we get square root of pi over 2 from this formula? I don't see how you would get any square roots appearing or pi's appearing if we're just starting at a half somehow. Well, turns out we can get 1/2 factorial to be equal to square root of pi over 2, but we have to be clever about it. We got to be sneaky. And how we actually define the factorial function when the thing we're taking the factorial of is not actually an integer to start. It's not one of the numbers like 1, 2, 3, 4, 5, etc. So today we're going to be talking about how would we actually go about computing something like 1/2 factorial, and why on earth would we try and use integration techniques somehow in a way to help us determine that. But before we do that, I want to talk about one kind of major way in which we can actually use factorials. That being the formula n choose k, where it turns out, and here's a theorem, the number of ways to make a set of k objects from a set of n objects is going to be given by the formula n choose k, which is usually written by kind of, you have these big parentheses and then an n over a k, but no bar in between because it's not a fraction, well, not explicitly. And we read this off as n choose k is going to be given by the formula n factorial over k factorial times n minus k factorial in our denominator. And what that actually allows us to do is this formula shows up all the time in math. It's commonly used in a branch of math called combinatorics. which is a branch of math that's about counting things. Yes, there is an entire branch of math devoted to counting things. Count Von Count would be proud. And no, it's no, it's not a super easy basic area of math. There's actually really hard questions to ask in the field of just counting things. But if we do a quick example here, if you just want to squeeze this in at the bottom of the page, it'll be a pretty small one. Let's say we have 10 socks. You go into your sock drawer one day and you see 10 socks just kind of laying there, and you're a bit lazy, so you haven't actually folded them up, your socks up into pairs. They're just kind of lying there individually. My goodness, I can relate. That's how I usually do it. How many ways are there to make a pair of socks from these 10 socks? So if we have 10 socks, let's say we have S1, S2, S3, up through S10. And this is my attempt to draw some socks on the board. How many ways are there to pick out two of those socks? Well, one way is we could take, say, sock 1 and sock 2. That would form a pair. We could take, say, sock 3 and sock 7. That would form a pair of socks. Maybe not a pair of matching socks, but it would be a pair of socks. We could pick S8 and S10. But how would we actually compute the number of ways to pick out a pair of socks other than going through and counting every one of them individually? Yeah, Phoebe?
When you're talking about taking a pair, are you also referring to like the order you take them out in?
Order doesn't matter.
Okay.
So if I had the pair of sock 1 and sock 2, we're going to treat that the same as if I took the pair of sock 2 and sock 1. Right now we're just saying, how many ways are there to put your hand in and take out 2 of those 10 socks, and then you can decide after you take them out which one goes on your left foot, which one goes on your right foot, let's say. Well, yes, Kate?
Is it 45?
Say what?
45.
Indeed. Did you just count all of those right now?
Um,
How did you get 45 from that?
I just put into that equation.
Yeah, turns out that in order to do that, we just need to compute what is 10 choose 2. Because we are given a set of n objects, in this case n is equal to 10, and we want to say how many ways are there to choose 2 from those 10 different socks that we have to work with. And in order to figure that out, we would have to take 10 factorial over 2 factorial times 10 minus 2 factorial. Well, that's the same as doing 10 factorial over 2 factorial times 8 factorial, if we simplify a little bit. So, Kate, when you got 45 out of that, did you actually go through and multiply out 10 factorial in your head and 8 factorial in your head?
No.
Or how did you evaluate this without actually computing what 10 factorial and 8 factorial are equal to? Because those are big numbers, by the way.
Well, if there's repetition because you have 10 factorial, you know, beat every number lower than that, so you could just cancel the 8 factorial, and then you could just do 90 over 2, which is 45.
Yeah. So we have a little bit of a sneaky shortcut here, in that we're going to end up with, if we were to write out 10 factorial as 10 times 9 times 8 times 7 all the way down to times 2 times 1, and then we were to do the same with 8 factorial, we'd have a lot of factors that cancel out in the top and bottom. So specifically, we could write 10 factorial out as being 10 times 9 times 8 factorial. Owing to the fact that if you were to take 8 factorial, that would give you the rest of what you need for 10 factorial. 8 times 7 times 6 times 5, all the way down to times 1. So 10 factorial is going to be equal to 10 times 9 times just the plain old vanilla 8 factorial. And then we divide by 2 factorial times 8 factorial still. And then it turns out 8 factorial is a really big number. I don't want to try computing that in my head. I'll go dizzy and fall over. But we don't need to know what 8 factorial is. So we can give it the old swoosh swoosh. And so we just end up with 10 times 9 over 2 factorial. Maria, what is 2 factorial, by the way? Yeah, 2 factorial is just 2 times 1, which is just plain old 2. That was not so bad. And then if we simplify this, we'll get 90 over 2, which is 45. Meaning, if you have 10 socks in your drawer, the number of ways you can pick out a pair of those socks, where the order doesn't matter, comes out to 45. By the way, Phoebe, since you asked, if we wanted to consider it in a case where the order does matter, what we would just do is we drop the 2 factorial term, and it would just come out to 10 times 9 is 90 in that case. Basically saying we would take the 45 pairs we already have, and we could make 45 new ones by just swapping the order of the socks within that pair. But if the order doesn't matter, 45's the number of pairs we can make. And this is a common theme in the branch of math called combinatorics, the counting branch of math, is that in combinatorics, you have something you want to count. Say, like, how many pairs are there of 10 that you can make from 10 socks? You don't really want to go through and count each pair individually, because with 45 pairs, you could get to 45, but it would take you a while. So instead, in combinatorics, we have these sneaky ways of finding formulas like this that will simplify the process of counting for you. And by the way, if this is something that intrigues you, take discrete math. Discrete math, we do a lot of these sort of combinatorics problems. Any questions or comments about the factorial function, how it's defined, how it's used to do these sort of counting exercises? All right, so with that in mind, we're going to take a break from factorials for just a minute, and we're going to define something called the gamma function. So the gamma function is a function that says for x greater than 0, the gamma function is going to take in x as an input, and we'll write it out as gamma of x using the Greek letter gamma, the capital version. Sort of looks like a upside down L, or if you're feeling a little bit morbid, almost like a hangman's noose. We're going to define it to be the integral from 0 to infinity of t to the power of x minus 1 times e to the negative t dt. Which, if you look at that, isn't that a lovely look? Joanna, doesn't that look like a lovely integral right there? Yeah, totally. You're not at all fazed by the fact that A, it's an improper integral, type 1 improper integral going from 0 to infinity, and also from the fact that inside the integral we have t's and x's floating around. glad Joanna feels that way. Oh, well, I hope the rest of you do as well. So, don't worry. I'm not going to make you do super complicated versions of this integral or work with it a whole lot. But turns out this integral is related to the factorial function in a sneaky way. But before we get into that, let's compute a couple of values of this gamma function, just to see what it would look like if we had to evaluate it out. So let's start by just finding gamma of 2. So what we're going to do is to find gamma of 2, what we're going to do is we're going to replace all of the x's, where there's only one up right there, in our integral formula with a 2, and then we end up with an integral that's defined in terms of t that we need to solve. So we get integral from 0 to infinity of t to the power of 2 minus 1 times e to the negative t dt. Or, if we simplify just a little bit, integral from 0 to infinity of just t times e to the negative t dt. And then evaluating this integral becomes what I would consider a standard 6 question. It's an improper integral, and we're going to have to use an integration trick in order to evaluate this integral. But I could have asked you this on the standard 6 quiz, and I think this would have made for a reasonable question. A bit of a scary one, but a reasonable question. So, Rhoda, how would you go about evaluating this integral, do you think?
First you would make it a limit as r approaches infinity.
Okay, limit as r goes to infinity, integral from 0 to r, t e to the negative t dt. Okay, so that's how we would handle sort of the improper part, at least to start, is just integrate from 0 to r and then pull out a limit out in front. So how would you find an antiderivative of t e to the negative t?
You could do integration by parts and separate it and identify one thing as x and one thing as dv. Or sorry, u and one thing as dv.
Say, oh gosh, you're trying to throw some x's instead of u's into the integration by parts formula? That's why we do the James method and not the Rhoda method. Yeah, I like it. So turns out to integrate something like this is actually a lot like the first one on your quiz today. We can make this an integration by parts integral. Rhoda, what would you propose to be our u, and what would you propose to be the dv here?
T would be u and e to the negative t would be dv.
Yeah, we could get e to the negative t dt. Neato burrito. So if u is equal to t, that would make du equal to dt. And v would just be, I guess, negative e to the negative t. Because differentiating negative e to the negative t would give you negative e to the negative t times negative 1, which is just e to the negative t. So if we compute this, we'll get limit as r goes to infinity. Let's see, uv, so that'll be negative t e to the negative t, evaluated from 0 to r, minus the integral from 0 to r of v du, so negative e to the negative t dt. Oh my gosh, improper integral integration by parts. What a horror. We'll come back to this expression here in a second. This negative t e to the negative t evaluated from 0 to r. I'm seeing two minus signs, so I'm just going to go ahead and cancel out the negatives here. Minus negative stuff can just become plus integral of e to the negative t dt. Christopher, how would you integrate e to the negative t? Because we're going to need to find what that integral comes out to.
Wouldn't that just be negative e to the t?
Close. Negative e to the negative t, I think. Yeah. We just do the same thing that way same thing that we did to go from dv to v here to say that's going to just come out to minus e to the negative t. And then we'll evaluate all of that from 0 to r. Which, if we do that, it's going to give us a limit as r goes to infinity of negative r e to the negative r minus e to the negative r minus negative 0 e to the 0 minus e to the, well, 0. Nora, how would we go about finding the limit as r goes to infinity of negative r times e to the negative r?
You can plug in larger and larger values and see what it's approaching.
Yeah, see what it's, yeah, we could certainly do that. I'm going to rewrite this a little bit, these two terms as negative r divided by e to the positive r, and this will be a minus 1 over e to the positive r. And then this will be minus, 0 minus 1? Because e to the 0 is 1. Yeah, Nora, we could certainly try just plugging in numbers for r. See what happens if we take r over e to the r power. Joy, what function would you expect to grow faster? Our numerator here or our denominator? Meaning, in other words, is r going to grow faster, or is e to the power of r going to grow faster as r gets really, really big? You think r is going to grow faster? No, I'm not saying you're wrong. I've just clarified, so make sure I heard you correctly. Keep a little bit of quiet. Okay, why is r going to grow faster than e to the r? Oh my gosh, e is just a constant, about 2.71-ish.
So if you take it to the r power, I'm not sure.
Let's take a look. Nora, let's take your approach for a second and just look at a really big, big number. So let's say if we were taking 10 over, say, e to the 10th power. Nora, which one of those is going to be bigger, 10 or e to the 10th, do you think?
E to the 10th.
I think so, because if you take 2.71 and you multiply by itself 10 times, 2.71 times 2.71 times 2.71, etc., if you do that 10 times, you're going to get a number that's a lot bigger than 10. Carson, how about 100 over e to the 100? Which of these is going to be bigger, the numerator or denominator? Yeah, denominator. In fact, it'll be a lot bigger than the numerator. Because if you're multiplying 2.71 by itself 100 times, you're going to get a really big number. Way bigger than whatever 100 would be. So, sorry to disagree with you, Joy. I actually think e to the r is going to grow a lot faster than r itself is. And in fact, this limit is going to go to 0 as r goes to infinity. Nolan, how about as r goes to infinity, what's going to happen to 1 over e to the r?
It's going to go towards 0.
Yeah, 1 over really, really, really big number, which as r goes to infinity, e to the r gets really, really big. 1 over really, really big gets really, really small. So this one will go to 0 as well. And so our final answer then is going to be something like 0 minus 0 minus 0 minus 1 Turns out it just comes out to 1. So that if we were to plug in x equals 2 into this formula up here, what we would get is just overall value of 1. Yes, Kate.
I'm sorry, how did we derive that formula?
This formula?
The gamma function.
That's just, how do we derive that? We don't derive that for anything, that's just a definition. We're defining the gamma function to be equal to that. If your question is why would we want to define that a formula like that, the answer is something something probability function something something. It's complicated. But also, it's going to turn out that defining the gamma function this way is going to lead to some really neat properties here in just a second. So if we were to keep going, gamma of 2 is 1, we would actually get, and this time, and I'm not going to make you evaluate all of these, but we would get gamma of 3 is equal to 2. Gamma of 4 is equal to 6. Gamma of 5 is equal to 24. Gamma of 6 is equal to 120, and so on. Where you could evaluate each of these if you did double integration by parts, triple integration by parts, quadruple integration by parts, quintuple integration by parts. Does anybody notice a pattern looking at these numbers? I'll squeeze gamma of 2 is 1 in there. 1 to 2 to 6 to 24 to 120. Gamma of 7 would be 720. Does anybody notice a pattern? What's happening as we go from one number to the next in this sequence? Kate?
It's raising by the same degree as the factorials. It's like the gamma of a number is equal to the factorial of the number below it.
Yeah. We multiply by 2 to get from 1 to 2. We multiply by 3 to get from 2 to 6. To get from 6 to 24, we're multiplying by 4, multiplying by 5, multiplying by 6, and so on. Which, by the way, is how I was able to rattle these off at the board. No, I don't have Kate's power of mental math. I didn't try and do a quintuple integration by parts in my head. So it turns out, trying to evaluate this gamma function, at least for an integer value, is going to be not so bad. Because here's a theorem that relates the gamma function and the factorial expression. Is that given any positive integer n, gamma of n is going to be equal to, Kate, as you pointed out, n minus 1 factorial. So for instance, if we wanted to evaluate gamma of 7, we would just need to evaluate 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. And that would give us 720. You could do this by 6 integration by parts. If you do that, good luck. Or you could just do a factorial. Take 6 times 5 times 4 times 3 times 2 times 1, which is still a little bit of work to evaluate what that is. But I would probably say it's a lot less work than trying to do a 6-tuple integration by parts process. How are we doing that time? All right, you all ready for this? We are going to prove this fact right now. That for any positive integer n, plugging in into this, plugging in n for x into this formula is going to give us n minus 1 factorial. Before I start proving that though, does anybody have any questions about what this is saying, what the gamma function is saying, how we're defining factorials, etc.? Alright, here's a question. Who here has played with dominoes at some point in their life? A lot of you have? I don't know, I think dominoes are pretty fun to play with. You can line them all up, knock one down, and it knocks the rest down. You can have them go up and down like little staircases and stuff. You get into a lot of mischief involving dominoes. Keep out of reach of young children, please. What we're going to do is we're going to prove this theorem using a mathematical technique called induction, where mathematical induction is essentially the same as setting up and knocking over a line of dominoes. And here's how that works. The whole idea behind induction is to prove a statement is true for, say, n values of n going from 1 to 2 to 3 to 4, etc., and so on. You do two things. The first thing you do is you prove it's true for n equals 1, which we'll often call the base case of your induction argument. And the second thing you do, and this is called the induction step, and this is the tricky step, is you assume that it's true for some n equals k. Assuming it's true for n equals k, prove it must also be true for n equals k plus 1. This is called doing the induction step. And here's the cool thing. Doing these two things will prove it's true for any value of n in the positive integers. For n equals 1, n equals 3, n equals a billion. Doing these two steps will prove it that the statement has to hold true for that. And the reason why is, well, we're proving directly that it's true for n equals 1. In terms of dominoes, that's like knocking the first domino over. And then the second step, the induction step, proving that if it's true for k, it must also be true for k plus 1. What that's like saying is, if you knock over the first domino, that's going to knock over the second domino. If you knock over the second domino, that's going to knock over the third domino. If you knock over the third domino, that's going to knock over the fourth domino. That's how knocking over a row of dominoes works, right? Well, the key idea here is we're proving it's true for n equals 1, and then assuming it's true for some k, prove it's true for k plus 1. Well, if it's true for n equals 1, then it must be true for n equals 2. If it's true for n equals 2, then it must be true for n equals 3. If it's true for n equals 3, then it must be true for n equals 4. And so on. So that by doing these two steps, where the second step is the equivalent of lining up the dominoes close enough together so that knocking one over knocks down the next. And then the base case corresponds to knocking over the first domino. If you do that with a stack of dominoes, you end up with all your dominoes are falling over. If you do that as part of a mathematical proof, what you get is your statement has to be true, not just for 1, but also for 2, 3, 4, and so on. And what I'm going to do is I'm going to apply this process to prove this theorem. Any questions or comments about that, about what induction means? No, I'm not going to make you all write proofs by induction. If you keep going on in math though, you will write proofs like this of your own. Because induction shows up a lot in higher level math. It's a very useful technique to have tucked into your mathematical tool belt. So let's prove this. So the first thing we need to do is our base case. We need to prove that this statement is true in the case where n is equal to 1. Meaning, we need to show, in other words, that gamma of 1 is going to be equal to 1 minus 1 factorial. By the way, James, can you remind us, what did you say 0 factorial was equal to?
1.
So we need to prove that gamma of 1 comes out to 1 as our base case. That's going to be the equivalent of knocking over our first domino in the mathematical proof process. Alrighty, well, gamma of 1, by definition, is going to be integral from 0 to infinity of t to the power of 1 minus 1 e to the negative t dt. Sarah, what is t to the 1 minus 1 power going to be?
So that's gonna be t to the 0.
And what is t to the 0 simplify to? Yeah, so t to the 1 minus 1, actually we can just ignore that term because it just comes out to a multiple of 1. So we end up with limit as r goes to infinity, integral from 0 to r of just plain old e to the negative t dt. That's something we know how to evaluate. Christopher, I think earlier you said that came out to just negative e to the negative t. So this will give us a limit as r goes to infinity, negative e to the negative t from 0 to r, which is the same as limit as r goes to infinity of negative e to the negative r minus negative e to the 0. We can write this as limit as r goes to infinity of negative 1 over e to the positive r, and this just simplifies to plus 1. And Mary, as r goes to infinity, what's going to happen to negative 1 divided by e to the r?
It's gonna approach 0.
Yeah, well, let's get a constant numerator of 1. Our denominator is going to get super, super, super big. So the fraction as a whole is going to go to 0. And wouldn't you know it, we got the value we wanted to, which was 1 in the end. We have proven our base case by showing this formula right here happens to work out in the case that n is equal to 1. Neato burrito. So our next step is the trickier one, the induction step. So before we move on to the induction step, does anybody have any questions about what we did as part of our base case, proving that if we plugged in n equals 1 into this formula does check out? Aiden, Bethany, y'all good? Fantastic. Nora?
I know you said that 0 factorial is equal to 1 just by definition, but 1 factorial is also equal to 1, right?
Yes.
So then how are they equal, I guess?
Why is 0 factorial equal to 1 factorial? Well, you can have a lot of functions that repeat output values, like say x squared. Nora, can you give me 2 values of x that when you plug into x squared will give me an output of 4?
2 and -2.
Yeah. So it turns out that the factorial function and the gamma function for that matter are kind of both examples of functions that have this property that you can have 2 different inputs that lead to the same output. That happens all the time in math. That just means your function is not 1-to-1, so to speak. And sometimes it's nice to have functions that don't repeat output values like x squared or the factorial. Because functions that don't repeat outputs you can take the inverses of, which we sort of talked about back in standard 5 with inverse trig functions. But the fact that 0 factorial and 1 factorial both come out to 1 is something that's generally not seen as too big of an issue. What would be an issue is if we had something like, say, 1 factorial came out to both 1 and 0. The same, if one input maps to 2 outputs, that's a big issue. That means it's not a function. But having 2 different inputs map to the same output, that's generally not considered to be a huge deal. Good question though. All right, so here's our induction step. Y'all ready for this? So in our induction step, we're going to assume the statement holds true for n equals k. I.e., we're going to assume that gamma of some k is in fact, which by definition is integral from 0 to infinity of t to the k minus 1 e to the negative t dt. We're going to assume that that comes out to k minus 1 factorial. And with that assumption in mind, we're going to prove that if this assumption is true, then it's also going to have to be the case that if we plugged in k plus 1 for n, it would also satisfy this formula. So with this, this assumption, we need to prove then that the statement holds true in the case that n is equal to k plus 1. Meaning we need to show that if this statement is true, that gamma of k is k minus 1 factorial, we need to mathematically prove it must also be true that gamma of k plus 1 comes out to k plus 1 minus 1 factorial. Or in other words, we need to prove that gamma of k plus 1 comes out to just plain old k factorial. Because if we can do that, then that, along with our base case, would give us a full inductive proof. Questions or comments about what we're doing before we write our inductive proof? Alright, so by definition, gamma of k plus 1 is going to be integral from 0 to infinity of, t to the power of, well, just k plus 1 minus 1, so t to the power of k, and I'll go ahead and write it out, t to the k plus 1 minus 1, e to the negative t dt, which we can write out as being a limit as r goes to infinity, integral from 0 to r, t to the k, e to the negative t dt. And we're going to do a little bit of integration by parts on this. We're going to, let's get rid of this u in dv for a second. We're going to let u, in this case, be equal to t to the k. dv is going to be equal to e to the negative t, which makes du come out to k times t to the k minus 1, using the power rule, dt. And if dv is e to the negative t dt, that would make v equal to, well, negative e to the negative t, as Christopher pointed out earlier. And so if we evaluate this, we'll get a limit as r goes to infinity, uv So negative t to the k, e to the negative t, evaluated from 0 to r, minus the integral from 0 to r of v du. So negative k, e to the negative t, k, t to the k minus 1 dt. This looks messy, but in truth it's going to be pretty nice here in just a second. You doing okay, Katie?
Yeah, there's just so many letters.
There's so many letters, I know. Don't worry, it's going to get a lot nicer in a couple lines from now. This will give us negative t to the k, e to the negative t. Well, the minuses will cancel out, just give us a plus. K is a constant, so we can pull it out in front of our integral to give us plus k times integral from, actually I'm just going to write this as plus k times the integral from 0 to infinity of t to the power of k minus 1, e to the negative t, dt. And James, what do we know about this integral right here? Or at least, what are we assuming about this integral right here? If we look back at our assumption on the bottom left corner there.
Oh, that it is equal to k minus 1 factorial.
Yeah, we're assuming that this is equal to k minus 1 factorial, because that just happens to be our gamma of k right there. Integral from 0 to infinity t to the k minus 1 e to the negative t dt. OMG. ROFLNAO. Which is going to come out to, I'm just going to say in the interest of time, this is going to go to 0. So our whole expression is going to come out to k times k minus 1 factorial. And just finally finish things off, Kate. Central Kate. What is k? How can we simplify k times k minus 1 factorial? So k minus 1 factorial is k minus 1 times k minus 2 times k minus 3, etc. What happens if we multiply all of that by k? We're going to end up with k factorial, the expression we wanted to get. Okay, we'll revisit this at the start of class Wednesday before moving on to standard 8, which will be arc length. But I thought I would introduce this to you as sort of a cool way of seeing, this is the sort of math proofs you write at higher level math. Is making these sorts of induction arguments, looking at these sort of counting theorems. This is all kind of a sneak preview of, if you keep going on in math, what awaits you. Have a good one. See you all, sorry to keep you a couple minutes over, but I will see you all on Wednesday. See you, Jason.